So as I'm sure you recall, we always split up the left side and the right side. We always split up the left side and the right side, work on them separately. We don't cross over. Sometimes when you look this stuff up online, people do that, which surprises me. So I guess this is a little bit of a cultural thing. There's some places in the States or around Canada or around the world where they solve these differently. But this is a pretty standard way for trig identities that we split the left side and the right side. And then we talked a lot when we did this about, what do you notice? Like, what do you observe? You got to look for like hints of things that are going on. But in this one, pretty clearly it's compound angle. So we're going to have to use those formulae to expand. And one of the tips is you typically work on the more complicated side. The right side, we have no idea where to go with that. There's no point in trying to turn it into something. So we're just going to work on the left side. We need to remember the formula. So the formula for compound cosine we're adding is cos x, cos y, change the sign, sine x, sine y, times all of that times cosine of y. Make sure you have brackets around that. It's really important. Plus, and then for sine, it's, again, I'm going to need brackets, sine x cos y, and the sign stays the same, plus cos x sine y. All of that times sine of y. And I know this is where people maybe start to get overwhelmed, not sure where to go next. But really, I mean, there's nothing I'm going to be able to do inside the brackets. If you could do anything inside the brackets, then our formula would look different. Like it wouldn't be that way. So there's nothing you could do. So really, the only thing you can do is distributive property with the cos y and the sine y. So we're going to do that. So I get cos x times cos y times cos y. So that's times cos squared y. That's important to notice. Minus sine x sine y cos y plus sine x cos y times sine y plus cos x times, again, sine y squared or sine squared y. Does anybody notice what's going on now? So these guys are the same. Sine x, sine y, cos y. Sine x, sine y, cos y. They're in a different order, but multiplication order doesn't matter. And one's negative, one's positive, so they add to 0. And I'm going to rewrite this next step. So I get cos x, cos squared y, plus cos x, sine squared y. And this is a step where it's really important to notice. This is like a big thing that it's hard for a lot of people to notice what to do next, I would say, but it's important. It's the step that we need, the last step we need to solve this. There's a common factor of cos x, and although we're very good at factoring, and in particular common factoring for polynomials, I think when it's trig, it's just not quite as obvious, But if I factor out the cos x, I get cos squared y plus sine squared y. And what does that, John? Yeah, that's the Pythagorean identity. Sine squared y plus cos squared y, or cos squared y plus sine squared y. So that's just cos times 1, which is just cos x, which equals the right side. So we're done. you remember this? Trig equations. This is one of the harder things we do in this course because there's a few different types, but they kind of look similar, and the different types, there's real different ways of solving them all, and if you don't really have that nailed down, then it's hard to know where to go. If you get off on the wrong, like if you start it wrong, it's gonna become a disaster really fast. This one's pretty straightforward. You can go ahead and start and try to get ahead if you like. So the first thing I'm going to do is bring the negative 2 over, set it equal to 0. And then this is like 5a squared minus 11a plus 2. And something you've seen from grade 10 forward is I can replace a with anything. I could replace it with a binomial, like x plus 7, or a trinomial, or like any polynomial, or a square root, or like a trig ratio, like cosine or sine or tangent or anything like that, right? I can replace a with anything, and the relationship still holds. The quadratic part of that relationship, of course, the whole thing isn't quadratic anymore, but there's in relation to like the a or the binomial, it's quadratic, and you can just factor it the same way. And sometimes people like to actually let a represent cos theta and sub a in and factor it that way, and then sub cosine back in. If you like to do that, that's fine. So I'm going to start with this. 5 is prime, 2 is prime, so there's not that many possibilities here. And I'm looking for something where where I put a 2 and a 1 in, and then it's going to add to 11. So I think I go here. 5 times 2 is 10, and 1 times 1 is 1. So they're going to add to 11. They're both going to be negative. So negative 1 times negative 2 gives me positive 2. And then 5 times negative 2 is negative 10. And negative 1 is negative 11. Okay? And I purposefully left that rest of that part blank. And that could be like my a or could be like my x. But in this case, that's the cos theta, right? So if that's the part that's confusing to you, we wouldn't usually write this 1 in there. If that's the part that's confusing to you, then do it a different way. Do it with a's or x's or something like that. But it's the exact same factoring principle. And then what do I get? I get therefore 5 cos theta minus 1 equals 0, or cos theta minus 2 equals 0. And that's just a zero product property like we've used so many other times. Two things multiply to 0, either one's 0 or the other is 0. For this one, that means if something minus 2 is 0, that something has to be 2. The only thing that minus 2 is 0 is 2. Cosine theta equals 2? Can't, right? We know from the graph that it can't. This is not possible. So there's no solution there. But this one, cos theta equals, move the 1 over, it becomes positive, divide by 5. Cos theta is 1 over 5. That's not a special angle, but that's definitely solvable. So if I take my calculator, finding the related angle, This just looks like one of the other questions we've already done yesterday in the review. But again, some people get to this step, and because of all the other parts of it, they sort of confuse themselves about what they're doing. Make sure your calculator's in radians. Shift cos 1 over 5, and I get 1.3694, and so on. Usually it doesn't say for this review, but usually we do 4 decimal places, if you recall. And then I have to do the whole cast thing and where, like, to actually solve this, right? Because all we found is the related angle, so I have to actually figure the rest out. And we showed that work yesterday, but in this case, cosine is positive in the first and fourth quadrant. So one of them is just 1.3694, and the other one is going to be 2 pi minus theta related to get to the fourth quadrant. So I'm leaving that answer, that exact answer in my calculator and doing 2 pi minus the answer so I get it exact, not rounded at all. So these are rounded in the end, but I'm not using any rounded answers, which is useful. It's a good thing to be able to do, right? Any questions about that? And then there's all the different types. We're going to see one more type, although it's a little bit simpler, but we're going to see one more. And but there's like the ones where you have to use an identity to switch, or the ones where you common factor, or like there's all sort of different types that you can do for these trig equations. This is the next one that we're going to do, yep. Sometimes when an equation is in the words, people just misread it. They miss like part of the equation, so be careful. That's why I was kind of underlining it. Like if tan 2 theta equals that, find theta. So it's that 2 theta part that makes this trickier. But we don't really have to worry about that until the end. Sometimes these have more parts to them. This one's sort of set up so that we can cut straight to the chase here. But so what I'm going to do to start is find 2 theta related by just doing shift tan of 0.7138. And this is 0.61992 rounded up to 3. Now there's two possible. Now what we can do here is we can think about the quadrants. So this is tan, it's positive. So it's going to be quadrant 1 and quadrant 3. That's where tan is positive, right? This part right here is positive. That's what we're talking about. So that means 2 theta is that number. And 2 theta is also that number plus pi, or pi plus that number. Seven, 6, 1, 5, 2. I'm going to divide both of these by 2 to get theta. Everybody good with that part so far? So all of that is mostly the normal thing that we would do if it was just theta, except we ended up dividing by 2 in the end, but that part's pretty simple. Everybody got that? But then there's a whole nother step. Now, it doesn't take a lot of work, but there's a whole nother step here that requires some sort of thinking, and we talked about like why we have to do this last part. So, and it has to do with this idea. There's a few different ways you can think about this, but this is how we did it. We're supposed to find where that equation is true within that domain or that interval from 0 to 2 pi. And usually we have 2 solutions in that domain. But what we did was we thought of this as a transformation. And 2 theta as a transformation compresses your graph. So if you normally had 2 answers in that interval, we're now going to have 4 because the graph is going to happen twice in there. Do you remember that? Is that coming back to you? So we've got so how do we find the other 2? If we've got these answers, we add pi to get the other 2 answers. And this one works out to 3.4516, and this one works out to 5.0224, and then we usually write these out just to be clear. We've got 4 solutions. Any questions about that? Okay, we're going to skip 5 and 6. So that's it for trigonometry. We got a couple more examples here that we're going to do for polynomials, and then we'll be done. We've been doing some difference of cubes recently, so hopefully this is familiar, or although there were a lot of people on the test. Oh yeah, I got to give you your test back. I'll do that after. That made a pretty big mistake in factoring the difference of cubes that was on the test, or there was came up a couple times. It's too bad, because we did a bunch of those examples in class. But make sure that you know this is something that comes up. It came up over and over again throughout the whole course, so it's obviously pretty important. And it's just a formula. So you take the cube root of the first term, cube root of the second term, and the first bracket, that's a binomial, shares the sign. So if it's a sum of cubes, the binomial bracket is plus. If it's a difference of cubes, the binomial bracket is minus. The first term is the first term squared, so y squared. The last term is the second term of your binomial squared, so in this case 4, and it's always positive. And the middle term is this times this, and it has the opposite sign. So that's your formula. It's literally a formula. You got to memorize it. But there are little tricks like you could expand to check that it makes sense to get the sum of cubes or the difference of cubes, the middle terms, all those middle terms have to add to 0 to go away. This is what a lot of people had something like this, y plus 2, so they got that part right, but then they had y squared plus 4, and that makes no sense. If you think about expanding that, it's not at all going to work. Okay, so be careful. I'm going to change this question. This question is a disaster. If you did it, good for you. You can check your answer because I have the answer here, but we'll do something still a little bit tricky, but a little bit nicer. X plus 2 cubed minus x minus 3 cubed. So this is a difference of cubes, but with a binomial. This is just testing our algebra skills. I remember there was a question like this on the test, and it was actually pretty well done, but some people, you miss a sign here or there, you expand slightly wrong, and then things don't quite work out. But it is a difference of cubes. It's a binomial cube minus a binomial cube, so we use the same formula. It's going to be pretty long, so make sure you have some room to write the whole thing out. So the first bracket is the cube root of the first thing. The second is the cube root of the second thing. And it shares the sign. And then in the second bracket, I've got the first thing squared and the last thing squared. And then the middle term is the opposite, and that's going to be plus. This is the opposite sign from here. And it's the first thing times the second thing. So I get x minus x, which is 0, and 2 minus negative 3, which is 2 plus 3, so that's 5. So I get just a 5 in that bracket. And then this is the part where you have to expand this disaster. So x plus 2 all squared is x squared plus 4x plus 4. Again, if you can do, you see how important it is to be able to expand a binomial the fast way. Back in grade 10 when you learned this, some people did, some people didn't, and it was fine not to do it this way. But by the time you get to functions, and then soon if you're starting calculus, the more little tricks that you can do to save yourself some time and is obviously the better. And then this one's going to be plus x squared minus x minus 6, and the last one is going to be plus x squared minus 6x plus 9. Looks like I've got 3x squared, 4x minus x minus 6x, 4x minus 7x is minus 3x plus 7. This question, the instructions will be factor fully, so don't multiply the 5 through. We want to factor. There shouldn't be, but if there was another common factor, or if that was factorable, you could check the discriminant to see if that's factorable to make sure you factor fully, but I think we're done. Any questions? Okay. So again, we're factoring. There was a big skill that we learned during this unit, Unit 3, factoring higher degree polynomials. We learned the few little things that are needed, remainder theorem, how to divide polynomials. We have two different ways of doing that. Then remainder theorem, factor theorem, which we're going to talk about in a moment, right? In order to factor any degree polynomial. So you could factor very high degree polynomials, but we saw mostly degree 3, degree 4. This one's just degree 3, so it's not too many steps, but degree 4 is the same process if you recall. And so there's a few different ways you can show your work, but I'm going to do it sort of the formal way. We're going to let f at x be this thing. And then what factor theorem tells me is that if I evaluate that expression at some number, and that gives me 0, I have found like a linear polynomial factor of that expression in this case. You could call it a function, but if it's f at x equals, but of that expression, right? So we're trying to find something like x plus 1, x plus 2, x plus 3, x minus 4, something that divides into that evenly, that has no remainder. Remember, remainder theorem tells us one thing, but it's factor theorem that helps us actually divide. So I noticed that 5 plus 3 is 8 plus 4 is 12. So if I put 1 in for the x's, I'm just adding the coefficients, and that gives me 0. So f at 1 equals 0. Therefore, x minus 1 is a factor. And there's a trick that you can use to just getting this part. And if you've gotten used to that trick, then oh my gosh, it saves you so much time. It saves you space on your paper. Just you don't have to, right, do the synthetic division part. But let's go off to the side and remember how to do synthetic division. So I start with the thing that I'm dividing, and I write down the coefficients: 5, 3, negative 12, and 4. And if there's a ghost term, so I've got the cube, I've got the squared, I've got the linear term, and I've got the constant, I've got them all. But if there was a ghost term, if there is a missing term, I'd have to put a 0 in. Don't forget that little trick. I bring this one down, and then I multiply by that value there. So this is negative 5. Then I subtract. 3 minus 5, minus negative 5, sorry, is 3 plus 5, which is 8. Then multiply. Negative 12 minus negative 8 is negative 12 plus 8, which is negative 4. Multiply by negative 1, and I get 4, which I better because that is supposed to be 0. That's my little check that the factor that I found worked, and I've probably done everything correctly because that worked out to be 0. It should. That's my remainder, and if it's a factor, your remainder will be 0. And then I have to be able to read the answer. It's those are the coefficients, and I have to kind of know that it's going to be a quadratic, because when I expand this, I should get back that. We're not done yet because we have to factor the last part. So what's it going to be? It's going to be plus 2 and minus 2. So it's 10 minus 2 gives me positive 8. Okay, any questions about any of that? The other stuff we did in this unit was all about graphing, so we're going to review a little bit of that right now. But there were a few other aspects to it. We talked about the properties of these graphs. we talked about end behavior and that sort of thing. So there's a few other details to this unit that we haven't quite covered in the review, but it was learning how to factor higher degree polynomials and learning about graphs of polynomials. That was the main part of this unit. So graphs of polynomials, remember, it was things like the leading coefficient and the degree tells me about the end behavior. Are they both pointing up? Are they both pointing down? Are they pointing different ways? Right? And in expanded form, you could get that much, but then in factored form, we could actually sketch graphs, or we can use the graph to come up with sort of the factored form of this polynomial. What do I know about the degree of this polynomial, the polynomial of this function that is in the graph, just by looking at it? Yeah, it's even. So I know all even polynomials, degree 2, degree 4, degree 6, degree 8, and so on, either point up or point down. And they're both pointing up, so the leading coefficient must be positive. But that will work out in the math. I don't have to worry about that. That'll work out in the math. Odd degrees, one end points up, one end points down, and again, the leading coefficient tells you which way. So what can I get from looking at the graph? I'm going to do this. I'm going to say y equals, and this is the part on the test that some people forgot. You got to put in the a. This is called the family of functions. You don't need to know it by that term, but it's called the family of functions, where I don't know the specifics of the leading coefficient, but I know about the roots or the x-intercepts. So this one is 3, negative 3, which means it's x plus 3. And the order of the polynomial, remember talking about that? The type of x-intercept this is a turning point. So that tells me the order of this is 2. Really important. Then I have this one at negative 1. So that's times x plus 1. And that order is 1 because it's a linear x-intercept. It's a straight pass-through. And then this is at positive 1. So this is x minus 1. And it's a cubic twist. So the order is 3. So it's got an exponent of 3 on it. Okay. And the a part is important because I don't know the coefficient. But all I need is 1 point. You might think that looks like a point, and it might actually be, but we don't know that for sure. It probably isn't. So usually you're either given a point, it's written out for you, or if it happens not to be, then you know that the y-intercept is fair. Like, you can't tell by the graph that that's negative 3 exactly, but it's safe to assume that it is. So this point is 0, negative 3. So we sub that in. Negative 3 goes here. And 0 plus 3 is just 3. 0 plus 1 is 1. 0 minus 1 is negative 1 cubed. So negative 3 equals, that's 9 times 1 times negative 1. Negative 1 all cubed is still negative 1. So this is negative 9a. And then I bring that over to the other side. So a is a third. And notice how, again, it worked out. It's positive. Like, I don't have to worry about that. The math will make sure that works out. If I got a negative answer there and the graph looks like it should be positive, I've done something wrong. And then it says determine the equation of the following function. So you have to rewrite this.